Make myself. Okay. Well, so we've been working through a lot of the simpler cases of differential equations. We've gotten to the point where we're actually dealing with differential equations that model um, physical systems that are interesting. And so what we're going to do today is just work through a couple of examples uh, of some of these ODEs. So I'm going to start off by writing out the problem. And then what I'm going to do is kind of go in steps and give you a chance to work through parts of these one piece at a time. Okay, so the differential equation that we're going to look at is 2y double prime plus y prime plus 2y equals g of t. So this will model either we can think of it as a mass on a spring with some kind of damping force. And then there's a driving force over here, or we can think of it as a charge on a capacitor in a circuit with a certain amount of resistance, capacitance, and inductance. Okay, so the driving force or the driving function is going to be well, let's write it like this. It'll start off at 0, going from time 0 up to time 5. Then it'll switch to 1 from time 5 to time 20. And then it'll switch back to 0 for t greater than 20. So this is our ODE, and then our initial conditions are the function, the solution is equal to 0 at 0, and derivative is equal to 0. So we might think of this as either a mass that is initially at its equilibrium position and has no velocity, or equivalently, the charge on a capacitor in a circuit where it's initially discharged and the initial current passing through it is 0. So charge counting the number of electrons, current measuring the flow of electrons. So the first step that we can do in a problem like this is rewrite our driving function, g of t, in terms of the step functions that we talked about yesterday. So I'll give you a chance to do that. If you could, let's see, how do you do this? Hopefully you know how to do this. You can do like a thumbs up. You know what I mean? In Zoom. Whenever you've got it, just do the thumbs up thing. And if after like maybe a minute still working on it, I'll just say my solution. Well, that was fast. I didn't even have time to eat anything. Okay, so I have that this is off until time t, so it will start off as 0 and then it'll go up to 1. So that will be at time t is equal to 5, so u5 of t. And then it'll go down by 1 at 20, so u20 of t. Okay. Now the next thing that I might do is uh, compute the Laplace transform of both sides of the differential equation. So maybe it would help if I put it so it's still in view. Okay, so of course this involves all of the terms on the left and right hand side. So all of this stuff over here, all of this stuff on the right hand side, and it will also involve the initial conditions. Okay, so same thing, wait for a thumbs up. You can also give me a thumbs up if you get sick. Are we ready for the solution? Okay. All right. So I'm going to write it in terms of capital Y. So let me cancel the screen so I can see it. So we'll have 2 times the Laplace transform of Y double prime. It would be S squared capital Y minus S times, right. Let's just write it as Y0 minus Y prime 0 plus S times capital Y minus Y0 plus 2 capital Y. So that's what I get for the left side. And then I need to get the Laplace transform of each of these. So this will be e to the minus 5s over s minus e to the minus 20s. Should be s over s. And now I'm just going to rewrite a little bit to clean this up. S squared y. I'll just go ahead and collect all the y's together. So that'll be 2s squared plus s plus 2 y. And then for all of the initial conditions, these are all equal to 0. So basically done with that. And on the right-hand side, I'm going to write 1 over s times e to the minus 5s minus e to the minus 20s. So if I solve for y here, which I could write as the next step, might as well. Solve for capital Y. Well, this is straightforward. Y is equal to e to the minus 5s minus e to the minus 20s over s times 2s squared plus s plus 2. Now, we want to get the inverse Laplace transform of this. So that would be the next thing that we're trying to do. It would be helpful if I did a little bit of rewriting. So I'm going to rewrite this as, because we know that these exponentials that are being multiplied by this fraction are just going to result in a shifting of our solution. So I'll rewrite this as e to the minus 5s minus e to the minus 20s times, I'm going to call this capital H of s. And so capital H of s is just going to be what's left over. So this is the 1 over s times 2s squared plus s. So when we take this and turn it into H of s, then we're going to get y is equal to something in terms of this H of s. So I think maybe a good next step would be to rewrite or to write our solution y in terms of this H of s. So what is that going to look like? Before we go on to the step of figuring out what this lowercase h actually is, let's write our solutions in terms of that. I didn't see any thumbs up, so I'm just sitting. Are you good? Okay. Just use that react thing so that I know I can move on. Okay. So whatever we have h of s is, it's going to be shifted forward by 5 and by 20. So what we'll have is u5 of t h of t minus 5. All right, this should be in terms of t. Doesn't really matter, it's just a variable, but that's the convention we use. And then u20 of t, h of t minus 20. So that's the shifted version. All right, now, well, one of the harder steps in this, I mean, it's not really that hard, it just takes some work. Let's rewrite h of s as the sum of two fractions using partial fraction decomposition. Maybe that's what you were already doing if I was waiting. So you're going to just immediately hit me with a thumbs up. I have to start working. Right in the middle of the bite, perfect timing. So I'm going to rewrite this s plus 2s squared plus s plus 2 as a over s plus bs plus c over s squared or 2s squared. Didn't need to erase that. 2s squared plus s plus 2. Clearing denominators, I get 1 is equal to a times 2s squared plus 2 plus bs squared plus cs. I'll go ahead and distribute that one out. And so what I get is 2a plus b s squared plus a plus cs plus 2a. And so I get 2a plus b equals 0, a plus c is equal to 0. And if I'm making mistakes, please feel free to just jump in and tell me I'm wrong. I will not be offended at all. Okay. Actually, I'll be quite pleased. So a is equal to 1/2. C is equal to negative 1/2. And what does that give us for b? B should be negative 1. Does this match my notes? Yes, it does. Okay. So we get that h of s is equal to let's just write it 1/2 over s. plus minus s minus 1/2 over 2s squared plus s plus 2. Okay, next step. What was I on? Step 4. So let's go to step 5. Um, well, figure out the inverse Laplace transform of these two fractions. So this will involve getting it into a form that fits one of the things that we have in our table of Laplace transforms. All right, 2 thumbs up. So let's see if I can do this. The first one, this one's a little bit easier than the second one. So I'm going to get 1/2 over s. Well, we know what 1 over s is, so it'll just be 1/2 of that. So this will transform or inverse transform. We'll write a little inverse Laplace above the arrow. This is just 1/2, right? Okay. Now this other one, um, it's going to be, well, let's see. I don't want to do partial fraction decomposition with this thing again using complex numbers. So what I'll do is that same sort of algebraic trick that we used yesterday, which is completing the square. So let's see. If I have minus s minus 1/2 over 2s squared plus s plus 2, then let's see, how do I want to rewrite? I don't want to have to do the details in my head, so I'll just write out the binomial expansion of this. So if I'm looking at this, then my a squared, you know what, maybe this would be easier. What I did was just factored out a 1/2. I don't have to quite think about it as much. S squared plus 1/2 s plus 1. So now I know that this is equal to 1/2 times minus s minus 1/2 over s plus 1/4 squared, right? Because that gives me 2 times 1/4 s, which is 1/2 s. So then I get plus 1/16, and this is 16/16, so I need an additional 15/16 to make up for that 1. I think that's what I got. Okay. Now, I'm going to split this into 2 fractions along the numerator. So 1/2 minus, let's just pull that minus out front. That's kind of a pain. S over s plus 1/4 squared plus 15 sixteenths. Multiplied by plus 1/2 over s plus 1/4 squared plus 15/16. I guess I could have done a little more rewriting that step. Okay, so I want something in the form s over s squared plus a squared. Maybe I should go ahead and do some rewriting here because I want this one to be in the form s, well, our s here is really going to be not really s, but s plus 1/4. That's the thing that we have squared. So I want my numerator to be s plus 1/4 too. So what I'm going to do is I'm just going to borrow a quarter from this 1/2. So s plus 1/4, and 1/4 taken away from this 1/2, I'm left another 1/4. So that's pretty good. This 15/16 I want as my a squared. The first one is not too bad. I get s plus 1/4. So that's really my s, my independent variable, and then my independent variable squared plus a squared. So I'll get square root of 15 over 4 squared. Now that's in the form of sine. So I'm going to consider myself done with that piece for now. And this other piece I want in the form a over s squared plus a squared. So s squared plus a squared. Again, going to be 15 over 4 squared. And the numerator I want to be square root of 15 over 4. Well, it's already 1/4. So I can make this a square root of 15 over 4. If I put a divided by square root of 15 out front. Now I can get the inverse Laplace transform of each of these pieces. So this one is going to transform by the inverse Laplace transform. do negative 1/2 times we'll do it in 2 pieces. I'll just have to remember to include that. Now let's do it in 1. So this will be cosine of AT plus square root of 15 over 4t, but it's also shifted by this 1/4. So we need to multiply by an exponential to undo that shifting. Let me rewrite that. So let's do the shifting first. So it's shifted by 1/4. So that factor accounts for our shift. This plus 1/4 here. And then you have cosine AT. Now this one just has a factor of 1 over square root of 15. And so that's fine. Or did I write cosine? Yeah, that should be cosine, right? Yeah, okay. Sorry. And then, well, this is shifted as well, so let's go ahead and count for the shifting. Sine of AT. So this is our h of t. Let's just put it all together now. The initial 1/2 minus 1/2 times e to the minus t over r cosine of square root of 15/4 t plus 1 square root of 15ths e to the minus t over 4 sine of square root of 15 over 4. So that's our whole h of t. I guess the last step would just be putting this all together. So I'm not going to write out the whole thing, reiterate. I don't want a rainbow. U5 of t, h of t minus 5, minus, yes, U20 of t, h of t minus 20, where this is our h. Now, like I said at the beginning, we're kind of approaching the point now where we're dealing, for a long time we deal with ODEs, and so these are sort of disconnected from any physical problems that we actually care about, that much. Now we're getting to the point where we're dealing with ODEs that can model physical systems that we kind of do care about or are interesting. And so once we get to this point, we start coming up with situations where the solutions to these problems, it involves a lot of writing. It involves there's a lot of pieces to this solution, but at least we're at the point now where we have all of the tools necessary to get this. Okay, so that's the first example, and I want to switch just a minute. I'm going to stop my screen share here, and I'm going to switch to Desmos. And let's actually look at what this solution looks like. So I want to make sure and show this because it took me a long time to get Desmos to do this properly. But what I have here is a definition for our step function. This one is only u0. So in order to use this for u5 and u20, I'm going to shift it by 5 and 20. So that's all that's happening there. Here is our h. Okay, so that's what we expected. And then it's chosen black here for this, so we'll look at it in black. But this is our solution. Now, an interesting thing to note about this is that although our forcing function is discontinuous, the solution that we get out of this thing is actually continuous. So I'm going to have to move you around a little bit. You can see the screen. This isn't actually a continuous function, and so this is something that we could think is, at least in that respect, is physically realistic. But you'll notice that right here at t is equal to 5 and t is equal to 20, it looks like we have sort of well, first of all, nothing happens for a while, and then we kind of hit the system with a force. So it hits the force and it kind of rings down for a little while, and then the force drops away and it drops back down to a new equilibrium position. And there's a little bit of a ring down here. And then it kind of settles down. There's the damping force that kind of settles down eventually to equilibrium with no movement. But it kind of looks like at these points where there are the discontinuities, like this might be a sharp point, like a sharp curve where there's no first derivative. But if we actually zoom in, we look at this pretty closely. You have to zoom in pretty far in order to see this. Center it so that when I zoom, there we go. You can see it's actually not a sharp point. This does actually curve kind of smoothly. So not only is this function continuous, but its first derivative is continuous as well. And if we went through all of the work, which I'm definitely not going to do, of computing the second derivative of this thing, we would find that it is, in fact, discontinuous. So this has a continuous function, a continuous first derivative, but the second derivative will be where we account for that discontinuity in our forcing function. That is a phenomenon that comes up in general when we have discontinuous forcing functions. That the order of the discontinuity, or what, so this is a discontinuity in the forcing function itself. It will show up in the highest order derivative of the solution for whatever order ODE we have. So this was a second order ODE, and so our second derivative has discontinuity in it. So that's some qualitative understanding of this problem. Now we could have actually worked this problem out in its entirety without using the Laplace transform. So if we can kind of zoom in on this and look at it. It has basically the form of things that we have looked at before. Let's actually switch back. No. So we could think of this as 3 different ODEs. So this would be our initial condition with it's at its equilibrium position and no velocity. And so for a while we expect the solution to just be 0. And then we hit it with some force. And so we could think of from here to here, we have some solution based on an initial condition. And so, well, we just get the solution 0 all the way up to here. And then we start a new initial value problem where we're starting from t is equal to 5. We're solving this initial value problem again with a position. Birds are going crazy. Initial condition and initial velocity 0. And then we solve just for the time interval from 5 to 20. And we could do that using the techniques that we had before, just as easily. Now, what we would need to do in order to go to the next step is that we would take that solution to the initial value problem, specific solution, and figure out what value it gives us at t is equal to 20. So what our initial condition for the third phase of this, its initial position and its initial velocity, and then solve another initial value problem for this last third right here. So the nice thing about this Laplace transform is that it allows us to take those three kind of separate problems and not solve them one at a time, but to do them all at once and get a common solution to all three of these pieces of the problem at the same time. So now let's consider another example. We have 15 minutes left, so I'm not sure how far we'll get through this one. Maybe I'll just work this one out. So let's go back to sharing screen over here. Go back to the whiteboard. And let's try something that kind of touches on the idea that we were just talking about how we get a continuous function. We have a function that is a continuous first derivative, but discontinuity is in its second derivative. What if we have instead, let's just give a simple ODE here, y double prime 4y. I looked away and screwed up my writing. 4y equals g of t, initial position 0, initial velocity 0, and our function g is going to be something like this. We call this a ramp loading. So we take the force to 5, 10, 15, 20. Okay, so our driving force or our driving function will be 0 up to time 5. And then it's going to go up to 1, but it's not going to be a step function. At 5, it's going to switch to a straight line. And it's going to go in a straight line. And then it's going to switch to staying at 1 for the rest of the time. So this g of t is equal to 0 for t from 0 to 5. Then it's going to be equal to 1/5 t times 5. So for 5 seconds, it's going to rise until it gets to 1. So that's a slope of 1/5. And we're going to shift this line forward by 5 so that it passes through this point, 5, 0, and then 1. So this is from I got these, can you call these backwards? Okay, so from 5 to 10, that's the sort of thing you're supposed to yell at me for. And then once we get to 10, it's 1 from then on. Okay. Now, this is a pretty straightforward problem to solve if we solve it using the methods that we had before. And in fact, we get a general solution. We can get a general solution for this. Well, let's not spend time going into that. Let's just look at using the Laplace transform for this thing. So we can rewrite our driving function like this. U5 of t times t minus 5. So we're going to be 0 for a while, and then we're going to switch to our linear function where we're climbing up. And then we're going to subtract away that linear function. When we hit time 10, we're going to subtract it away. So it's the same linear function, but shifted forward to 10. And that'll give us our ramp loading function. Okay. Now, if we take the Laplace transform on both sides, we'll really quickly do that. S squared y minus s times 0 minus 0 plus 4 capital Y. But we knew what this side was going to turn out to be. We worked this out several times. And now we want the Laplace transform of t minus 5. Well, there's just going to be a shifted t. And we know that t is 1 over s squared. Well, let's rewrite this. 1 over s squared. There's going to be this is going to account for the 1/5. And then in the numerator, we're going to have the two shiftings. So there's one that's going to shift forward by 5. That's e to the minus 5s. Now, which 5s and s didn't look so similar. And then we're going to subtract it away at 10 seconds. So we're taking it and shifting it forward. I'll clean this up a little bit so it's more like there. No mistaking that for an s. So this is what we get. And our y here is going to be equal to, let's factor out the stuff that doesn't look like polynomials in the denominator. So that is factor of 1/5 out in front, e to the minus 5s minus e to the minus 10s out in front. And then we're going to have a fraction 1 over s squared times s squared plus 4. So we've got a couple of quadratics here. Now we know that our solution is going to be 1/5 u5, well, h of t minus 5. I'm going to use the same notation as before, but then I'll write down what I actually mean by it. U10, I should write of t. U10 of t, h of t minus 1. We know what ut is a function of, but I might as well be consistent. So this part right here is, of course, using the same notation. This will be h of s. And then we'll take the inverse Laplace transform to get h of t, little h of t. So that's what that h of t will be. Partial fraction expansion. I always call it decomposition. I guess it doesn't matter. It's just a name. So we write this as 1 is equal to ax plus b. I should write out what I'm trying to do. 1 over s squared plus 4 is equal to ax plus b, or s squared plus dx plus d. If you remember back to Calc 2, there are a lot of tricks for doing partial fraction decomposition more quickly, but I don't like to memorize tricks. I like to, what's the opposite of memorize tricks? Forget them. Who knows? Anyway, just memorize one method and use it forever. So I get, and these should be not x's but s's. That's something I should remember. There we go. So I'm going to have cubic. So what I'm going to end up with is can I recover? Only one way to find out. This will be a plus c s cubed plus will be my squares, b and d. And then my linear terms, 4a, and that's it. The only linear term? Yeah. And then my constant term will be just be b4. Okay. So I get a plus c is equal to 0, b plus d is equal to 0. That's nice. 4a is equal to 0. Well, we've got a so far. We've got a and c. And then b4. What did I write? b4 is 4b. That's equal to 1. So a and c are equal to 0. B is equal to 1/4. D is equal to -1/4. Which looks like that. So am I out of time yet? No, 5 minutes. Okay. Well, go ahead and finish this off. So I get that our original h of s is equal to 1/4 over squared. It's a nice trick of writing I like to do. Use the slant instead of the bar if it's a fraction inside a fraction. You can kind of keep them separate. Minus 1/4 s squared plus. So what do we get for h t? 1/4 t. That's the straightforward part. Now the maybe less straightforward part. I want this going to be minus. That's okay. In order to rewrite this, I'm going to save myself a little bit of cognitive energy. What I want is 2 over s squared plus 2 squared. And I will have 1 over s squared plus 2 squared if I factor out that 1/4. So I just need another 1/2. And without much thought being applied at all, come up with sine of 2t. Very nice. So this has a sinusoidal component, but it also has this ramping that we saw before. So this ramps for a while, then it kind of dies out. So what was our y of t? We have this starting at t is equal to 5, and then it gets subtracted away at t is equal to 5. Now, that cancellation works really well for this linear part here, because a linear increase and then we're subtracting away a linear increase, that's just going to perfectly cancel out. However, for this part right here, we're going to have to think about maybe a little carefully. But this sine do I agree with the conclusion that I'm coming to? We're going to end up with a sinusoidal component. But when we subtract away this the sine from here with the sine from here, they're out of phase. So they don't perfectly cancel out, and we continue to have a sinusoidal oscillation. Now, what kind of throwing me a little bit is that if we timed that perfectly, if we timed the end of that ramping just perfectly, does that mean that we can get those two sines to cancel out? Is there a way to ramp this up so that when we hit that top, we don't have this continuous oscillation? It continues to go on after that. It's interesting to think about. Can we drive this oscillation just right so that when we stop increasing it and have it just as a steady thing, that it perfectly cancels out with whatever velocity it already had, and it just stays at that equilibrium. Well, all of this work that we've done does seem to imply that. That's something to think about. Are we out of time? Oh, just perfectly enough time for me to say that the solution that we get from this is continuous, just like we expected. Its first derivative is continuous. But now, because this thing, our driving function itself is continuous, our second derivative of the solution is also continuous. So we get continuity up to the second derivative. And it's actually in the third derivative that we lose continuity, because this one, although it is continuous, it has a discontinuity, or it has not a discontinuity, but it's a derivative as a discontinuity at these points because it's a sharp point, as you remember back from Calc 1. Those are places where we can't. Okay, I think that's enough for today. I'll stick around if you have any questions. Otherwise, I'll see you. Is it Friday yet? No, it's Thursday. I'll see you tomorrow.